Howdy everyone, I'm Seth Anderson and I am here to present our final process control dynamics project called The Fast and the Furious by Ashley Dahl, Jake Curl, and me, Seth Anderson. Our purpose in this project was to design a small robot car that would simulate adaptive cruise control. And adaptive cruise control is a modern feature in today's cars that allows for the driver to not only set a cruise speed, but also set a gap distance between them and the car in front of them. Once this gap distance has been set, the controller inside the car will maintain the speed for the driver in order to maintain that gap distance no matter how much the car in front of you slows down or speeds up. So here with the hardware that we use for the project, we have our CamJam kit car right here with our two wheels, two motors that are powered by this battery pack. In front we have our distance sensor, here's the transmitter, and then the receiver. That's how we get our distance measurement. All works into this breadboard as well as the motor controller up here, which then feeds into the Raspberry Pi. And our Raspberry Pi is powered by this power bank right here, which we decided to have the car drag behind it because we couldn't find any place to fit it on the car. And you probably noticed the big Duracell battery right here. That doesn't serve any purpose other than providing enough weight in the back of the car to balance the front so that the wheels have enough traction to propel the car forward. Here's our data, or our Python program we wrote in order to get a doublet data test. And as you can see, we started with a sleep function of 40 seconds to give us enough time to set up the car. And then we did 3 set point changes in the speed from 60% to 30, down to 0, and then up to 1 for the last second or so. So the way we perform the test is we had the car run through these set points while following a constant velocity object. The way we generated the objects, we originally planning on using an RC car, but we couldn't find one that worked still because all we had were toys from 12 years ago which had dead nickel cadmium batteries that couldn't hold a charge anymore. So instead, we used a KitchenAid mixer. We tied a string to one of these little prongs right here, and we had it wind up at a constant speed, and we pulled a box in front of the car to simulate a vehicle moving in front of it. Here is the result of that doublet test. And after performing that doublet test, we then performed a FOPDT regression, getting our values for Kp, Tau p, and Theta p. And here's the result of that FOP test. You can see our Kp value and Tau p value, Theta p value up there. We decided that this was a good enough fit and that would provide us a good start for tuning our parameters. And as far as tuning parameters, here's our PI controller. We decided to use a proportional integral controller because we didn't see any need for a derivative term. We did 600 points of measurement, and that is across, each measurement has a wait time of 20th of a second, so that ends up being 30 seconds of data. And we have our array set up, and we have our controller set up as well. We made sure to clip the outputs so that we wouldn't saturate the controller. And once that runs 600 times, the robot will stop and it'll load it onto a CSV file. And the result of our first attempt was obviously very poor. As you can see, there was very little set point tracking, and the car had trouble keeping up in any reasonable way with the quote-unquote vehicle in front of it. However, once we tuned the parameters and we figured out a better way to run the car, we eventually got fairly good set point tracking. As you can see, there's some offset with the set point tracking, and that is due to if the motor percentage is set below 25%, the motors do not have enough torque to turn the wheels. And so the car couldn't quite get to that last part of the 15 centimeters and then the 20 centimeter set point change because of that lack of power. So now I just want to go through a little video montage. Here we have one of our attempts at the doublet test. As you can see, we had some difficulty in controlling the box with the speed of the mixer, which you will see in just a moment. In this other test, you can see in my hands in the top right corner. Later on, when we were trying to tune the controller, we had issues with the car not going in a straight line because of drag caused by the battery dragging behind, as well as just imperfections in the chassis and in the wheels themselves. So we decided to try and push it up against the wall, which worked pretty well, but the issue was we ended up running into things like that, as well as you'll see in a moment, running out of wall. And we decided that it'd be better if, even though the wall gave us semi-good accuracy, we wanted to try and get it to go in a straight line, so we made some adjustments to the chassis, and as you can see, there were small improvements, but we still had issues with the car not going in a straight line and had difficulty keeping our box or the other vehicle in front of it. And even though we got pretty good data from those results, we tried to get better and better, and as you can see, we slowly improved. We need to make small adjustments, but eventually, through lots of tuning and lots of adjustments to the chassis and to the way the items were distributed, we ended up with one successful test where the car went in a straight line and tracked the box perfectly, which was that graph that you saw before. And so we'll end with this clip of the car following the vehicle in front of it, and this is our adaptive cruise control simulation project. Thanks for watching.